Alright, non-resident training course Steelworker Volume 2, Navy EDTRA 14251. Distribution Statement approved for public release. Distribution Unlimited. Chapters 3. Structural steel terms layout and fabrication of steel and pipe. Structural steel is one of the basic materials for the construction frame of the most industrial buildings, bridges, advanced base structures. Therefore, a CB steelworker must have a thorough knowledge of various steel structural members. Additional is necessary before any structural steel is fabricated, erected, or planned. Acts and sequence events be set up. The planned sequence required materials are predetermined by engineering section of the unit, then drawn up with a set of blueprints. Chapter describe the terminology applied with structural steel members, the use of members, the methods by which they are connected, and the basic sequence of events occurring during erection. Structural steel members you work with require use of various structural material members made up of standard structural shape, manufactured wide variety of shape, cross-section, and sizes. Figure 3.1 shows many of the various shape. Three most common types of structural members are the Y or wide flange, S-shape American Standard I-beam, and the C-shape American Standard channel. The three types identified with the nominal depth inches along web and weight per foot and length in pounds. An example of W wide gauge 12 by 27 indicates a W-shaped wide flange 12 inches deep and 27 pounds linear foot. Shows cross-section wears wide standard and C-shape differences between W-shape and so you have W-shape bearing pile, S-shape, C-shape, M-shape, miscellaneous shapes other than WS, SB, and SC. Channels other than American Standard. Angles, equal leg, unequal leg. T structural cut from W-shape, cut from S-shape, cut from M-shape, plate, flat bar, pipe structural. Our figure 3 shows the structural shape, the W-shape, the web, the flange width, the S-shape web, the depth of the flange and the web of the C-shape. The S-shape is designed for the inner surface of the flange. The W-shape of the wide flange shape has a parallel inner and outer flange surface with a constant standard thickness, while the standard shape has a slope approximately 17 foot inner flange surface. C-shape is similar to the standard shape. Is the inner or the channel shape that's similar to the standard shape of the inner flange surface is sloped approximately 17 feet. The wide flange shape is a structural member whose cross-section forms an H and is most widely. The structural member is designed so that a flange provides strength horizontal and plane, while the web gives strength in the vertical plane. The wide flange shape are usually beams, columns, truss members in or load-bearing applications. The bearing pile or the HP shape, almost identical to the wide flange. The only difference is that the flange thickness and the web thickness of the bearing are equal, and whereas the wide shape found a different web and flange thickness. The standard shape I-beam is distinguished in cross-section being shaped like a letter I. Standard shape is used frequently than wide flange, since standard shape possesses less strength and less adequate than wide flange. The channel shape, American Standard channel, has a cross-section somewhat similar to the letter C. It is especially useful location, single flat face without outstanding flanges on one side. Required channel shape is not very efficient for a beam or a column when used alone. However, efficient build-up and members may be constructed with the channels assembled together with structural steel shapes connected by rivets and welds. An angle structural shape cross-section resembles the letter L. Two types illustrated in Figure 3.3. Commonly, the equal leg angle, the unequal leg angle. Angles identified with the dimension and thickness of its legs. For example, angle 6 inch by 4 inch by half inch. Dimension of the leg should be obtained measuring along the outside back of the legs. Where an angle has unequal legs, dimension wire leg is given first, and the example is just cited. Third dimension example applies the thickness of the legs, which always have equal thickness. Angles may be used in combination 2, 4, or for main members. Single angle may also be used to connect the main parts together. Steel plate is structural shape when crossing section form a flat rectangular general main point. Remembered about plate is that it has about a width greater than 8 inches and thickness of a 1/4 inch or greater. Plates are generally used connections between other structural member component parts. Built up structural member plate cuts are specific size obtained with a width range of 8 inches to 120 inches or more, various thickness. The edge of these plates may be cut by sheared plates or rolled squared universal mill plates. Plates frequently referred to by this thickness, widthness, and length is plate 1/2 inch by 24 inch length of all cases given in inches. Note Figure 3.4. that 1 cubic foot steel weighs 490 pounds. His weight divided into 12 gives you 40.8, which is weight in pounds of a steel plate for 1 foot square and 1 inch thick. Fractional portions normally dropped. 1 inch plate is called 40 pound plate. Practice may hear the plate referred to as the approximate weight per square foot, specified thickness. An example of 20 pound plate, which indicates a 1/2 inch plate. See figure 3.4. The designation generally used flat steel have been established American Iron Steel Institute flat steel design for the bar and strip. Figure 3.3 shows equal legs and unequal leg angle. Iron 3/4 weight thickness in steel. Steel plate thickness 2.5, 1/2, 1 3/4, 1/2, 3 is and 1/4 from 80, 60, 40, 30, 20, 15, and 10. 1 cubic foot of steel, 490 pounds. Sheet plate according to the thickness of the material, the width of the material, and for some extent of the rolling process to which is subject to table 3.1 show the designation usually for the hot rolled carbon steel. The terms are somewhat flexible. Some case may overlap. Structural referred to as bar has a width of 8 inches less of the thickness greater than 3/16 of an inch. The edge of the bar is usually a rolled square. Like universal mill plates, dimensions are expressed in similar manner as for the plates. The instance of 6 inches by 1/2 inch bars are available in a variety of cross-sectional shapes: round, hexagonal, octagonal, square, and flat. There are different shapes illustrated in figure 3.5. Both square and rounds are commonly used with the bracing members of the light structure. The dimensions in inches applied to the side of the square and the diameter of the round. Now you have been introduced in various structural members using steel construction. Let's develop theoretical build frame for where your steel worker would start the project after all the earthwork, footings, and slab have been completed. Remember, the sequence of theoretical may vary. Alright, figure 3.1 shows plate, bar, strip, sheet designation, width in inches and thickness for bar, strip, plate, and sheet, somewhat depending on the type of the structure being erected. 3.5 shows the bars as flat, square, and round. Anchor bolts, figure 3.6 are cast in concrete foundations designed to hold the column and bearing plates, which are first members of the steel frame placed into position. Anchor bolts must be positioned very carefully so the bearing plates will be lined accurately. Bearing plate, the column bearing plates are steel plates, various thickness in which holes have been either drilled or cut with an oxygen gas touch to receive the shows the figure 3.6 shows the anchor bolts, the column fitting anchor bolt. Receive the anchor bolts. Figure 3.7 holes should be slightly larger than the bolts. Some lateral adjustment bearing plate is possible with the angle connections with the columns attached with the bearing plates bolted and welded in place according to the size of the column as shown in figure 3.8. After bearing plate has been placed in position, shim packs are set under the four corners of each of the bearing plate. Each of it installed over the anchor bolt is shown in figure 3.9. The shim packs are 3 to 4 inch metal squares, thickness ranging from 1 1/4 inch, 1 1/16 inch to 3 1/4, which are used to bring all bearing plates to the correct level and level each bearing plate of its own base. 3.6 shows the column bearing plate, the connecting angles for the column, the center punch mark, anchor bolt holes, and then figure 3.8 shows the type of column base connections. You have the welded base and anchor bolted, angles bolted to the web, and angles bolted to the flanges. Figure 3.9 shows the leveled bearing plate, anchor bolt, grout holes, shim pack, connection washer, and grout here. The bearing plates are the first level that individually adjust the thickness of the shim pack, with the operation accomplished by using 2 foot level around the top of the bearing plate, perimeter or diagonal across the bearing plate. Upon completion of the leveling operation, all bearing plates must be brought either up or down to the grade level required for structural steel being erected. All bearing plates must be lined up in all directions with each other. This may be accomplished by using a surveying instrument called a builder's level string line. May be set up along edges and tops of the bearing plates by spanning the bearing plates around the perimeter of the structure, making the grid network of string lines connecting all the bearing plates. After all the bearing plates have been set, with the line space between the bearing plate and the top of the connecting concrete footing and slab must be filled with a hard, non-shrinking, compact substance called the grout. In figure 3.9, when the grout has hardened, the next step is the direction of the columns. The columns, wide flange, remember the nearly square and cross section possible, most often found, all used in columns, large diameter pipe, also frequently figure 3.10, even though the pipe comes off the present connecting difficulties. When attaching other members to column may also be fabricated by welding and bolting a number of the other rolled shapes, usually angles and plates as shown in figure 311. The structure is more than 1 story high. It may be necessary to splice one column member on the top of another if required, but the column length should be. It shows 310 shows a girder span, pipe columns. 311 shows the built-up column section, shows the bevel of the weld and the cover plate and the web plate and the web. Figure 312 shows the column splice with no size change. You have shop rivets, field bolts, and wide flange 10 inch by 49 3/4 inch splice plate. Figure 313 shows the column splice changing the column size, 1 inch filler, 3/4 inch splice plate, the wide flange 8 inches by 31 inches, 1 bearing foot, wide flange 10 by 49. Alright, column splices joined together by splice plates, bolt riveted and welded with a column frame. Special cases, the webs as well, but the members are same size, common practice, but one directly over the other. Fashion splice plates over the joint, illustrated in figure 312, with the column size reduced over the joint and the plate, usually between 2 ends of the provided bearing filler plates, or even between the splice plates and smaller column flanges, figure 313. Alright, girders. Girders are primary horizontal members of the steel frame structure that span from a column to column, usually connected to the top of the columns with cap plates, bearing connections, as shown in figure 314. An alternate method is seated connection, figure 315. The girder is attached to the flange column using angles with one leg extended long across the girder flange, the other against the column. The function of the girder is to support the intermediate floor beams. So 314 shows the girder span wide flange column, shows the wide flange game column and the cap plate, bearing connection with another wide flange girder. 315 shows a seated connection, column, seated connection, and girder. Alright, beams are generally smaller than girders, usually connected with the girders and intermediate members of the to columns. Beams connecting columns are similar to the seat of the girder column connection. Beams are generally to carry the floor loads, transfer loads to the girder vertical loads. Since beams are usually not as deep as the girders, there are several alternative methods for framing one into the other. A simple method is to frame the beam between the top and the bottom flange of the girder, as shown in figure 316. If it is required that the top of the bottom flange of the girder beam to be flush, it is necessary to cut away the cope or a portion of the upper or lower beam flange, as illustrated in figure 317. 316 shows a column splice with no size flange, beam and a girder, and 317 shows a cope end and a blocked end. Bar joists. Bar joists form a lightweight, long-span system floor support, built-up roof support, shown in figure 318. Bar joists generally run in the same direction of the beam, many times eliminate needs for the beams. We'll notice figure 319 that bar joists must have the bearing surface. The span is from girder to girder, figure 320. Prefabricated bar joists designed to conform with the specific load requirements obtainable from commercial companies. Trusses. Steel trusses are similar to bar joists if they are severe, same purpose, if they look somewhat alike. However, they are much heavier and fabricated almost entirely with the structural shapes, usually angles and T-shapes, see figure 321. Unlike bar joists, truss can be fabricated to conform with shape, almost any roof, figure 322, and therefore more versatile than bar joists. Bearing surface of the truss, normally with the column, truss may span across the entire building from outside column to outside column. After the truss have been erected, they must be secured between bays with the diagonal braces normally. So here you see the bar joist, the girder, metal roofing, the linlets, the masonry units, column footing for not visible. Here it shows a bar joist seat connection. 320 shows installing bar joists girder to girder. Round rods, light angles on top of core plane, figure 323, bottom core plane 324. After these braces are installed, sway frame is part in place, figure 325. Purlins, girts, and eaves and struts. Purlins are generally lightweight, channel-shaped, and are used to span roof trusses. Purlins receive trills, other type of decking, as shown in figure 326, are installed with the legs of the channel facing outward, downward slope of the roof of the purlins, installed with the ridge and gable of the roof, referred to as ridded struts. Purlin units are placed back-to-back at the ridge and you tie together with steel plate, threaded rods, and illustrated in figure 327. Side of the structure is often framed with girts. Members are attached to the columns and horizontally. Figure 328. The girts are also channeled, generally same size shape at the roof purlins. Siding material is attached directly to the girts. Alright, shows this 321 shows a steel truss fabricated with angle shape members. 322 shows the different styles of truss shapes, and 323 shows diagonal brace top chord plane, purlin struts, diagonal brace roof truss. 324 shows diagonal brace bottom chord plane, roof truss, longitudinal strut, diagonal bracing. Alright, figure 325 shows sway frame, roof trusses, sway frame, and then 326 shows roof purling truss, channel over roof trusses, and then 327 shows rigid struts, space steel diaphragm, thread rods, purlins, roof truss. Figure 328 shows a wall channel with a wide fringe girder column. There are longitudinal members similar to purlins. The girt is a cave strut. The member is attached to the column point where the top of the core truss column meet the cave in the instruction figure 329. There are many more steel working terms that you will come across and gain experience. If the term is 329 shows the rough eave truss, shows the roof and then the channel eave truss, and so there are many steel working terms. If a term is used that you don't understand, ask someone to ask and look it up with the manuals and publication available to you. Steel workers are required to lay out, fabricate steel plate structural members assignments. You expect to be tasked include paper layout, fabrication projects, types required with a tank farm project, plate layout procedures similar to those for sheet metal. Chapter 2, there are some procedural plate fabrication, however they are fundamentally different. They are described in this chapter. Steel workers are tasked to construct and install piping systems designed to carry large quantities of liquid for long distances. Fabrication plate, structural member steel plate, much thicker than sheet steel, is more difficult to work than with and form in its desired shape. Before fabricating anything with steel, you must take into consideration certain factors to ensure have been planned for. First, ensure adequate lighting is available to enable you to see small marks you will be scratching on the steel. Second, ensure all tools you need available and accessible in the work area. Also, ensure you have accurate failed sketch shop drawing of the item to be fabricated. Layout of steel. When laying out steel, you should have the following tools: adequate scale, such as the combination square head, accurate protractor, set of dividers, prick punch, and a center punch, and a ball bearing hammer. When laying marks on made of steel, you must wire brush clean them, remove the residue with a brush or rag, repaint, and then paint this with a surface with a colored marker compound. Aerosol spray, very good because it allows paint to fall onto the areas to be laid out. Also, because it produces a thin coat of paint that will not peel off the lines which are described. When appropriate, layout lines can be drawn on steel stone markers, similar devices. However, remember the markings. Many of these drawings devices can burn off under acid gas flame. Well done, blown away, force oxygen from cutting towards these conditions are undesirable, can ruin an entire fabrication job. If using soap stone or similar marker is your only option, be sure to punch and ball peen hammer to make marks along the cut lines by connecting the dots to ensure accuracy. Plain material usage before starting layout plate. With example, the proper plate layout material usage shown in figure 330. Observe the material used with the cooling box. Take the slightly more half of the plate. Rest of the material can be used on another job. This is only an example, but the idea of conserve the material. The example of a poor layout shown in figure 331. Entire plate is used for the one product, wasting material, increasing cost and layout time of the job. A person must have a straight line or straight edge. He or she refers to all measurements as a straight edge. Straight line edge can be edge of the work and it has been finished straight. It can be outside straight line fastened to the work, such as a straight edge clamped to the work. Once reference has been established, you can proceed with laying out using procedures described in Chapter 2. When the layout is complete, the work shall be checked for accuracy, ensuring all parts are in the figure 330 shows a proper plate steel cooling boxes, side 1, 2, 3, 4, 2 stubs, top from bottom. Mount 1, mount 2, mounting brackets, toe stub, improper plate steel cooling box plan, side 1, side 2, mount 2, mounting brackets, top, bottom, side plate, toe stubs, and sides. So you've saved the plate on the top and you've used the improper plate steel box layout. And 331. Layout and measurements are correct. After the determining the layout is accurate with the layout, person should center and punch all cutting lines, ensure that accurate cutting with the H either torch or shears the work. can be checked after cutting because each piece will have one half the center mark on the edge of the material. Remember, always cut the curve of the torch on the outside edge of the cutting lines. Lay out structural shapes. Structural shapes are slightly more difficult to lay out than plate. This is because the layout lines may not be viewed in the layout person at all times. Also, a reference line may not always be in view. Steel beams are usually fabricated to fit up with another beam, and coping and slotting are required to accomplish. Figure 332 shows a wide flange 10 by 39 pound beam fitted up with beam A intersecting beam B. At the center, coping is required in seam A, so beam A will butt up to web B. Connecting angles again can be welded to the web, and flanges can be welded together. A cut 1/1/8 of an inch long at 45 degrees at the end of the flange cope will allow the web to fit up under the flange beam B. It is also a fillet size and cope determined divided by the flange width, receiving beam in half, and then subtracting 1/2 the thickness of web plus 1/16 of an inch. Determines how far back the beam A cope should be cut. When two beams are different size connected, the layout intersecting beam is determined whether it's large or small intersected beam. In case shown figure 333. So figure 332 shows fabricating fit-up joining of two beams the same size. Shows the two-fit under flange wedge. We have a wide flange 10 inch by 39 pounds. That's 8 by 10 inches on both width and flange, 5/16 of an inch thick. And you have a fillet allowance, and you fit under the flange of the web 1/2 inch, 1/2 inch web 1/16 of an inch. And that's part A and part B fabrication flipped. And then figure 333 shows typical frame construction top flange flush. Intersecting beam smaller, therefore only one flange is coped to fit the other. The top flanges will be flush. Note all the angles of the connection are to be bolted rather than welded. Connection angle layout. Every very common connection with a frame construction connection angle. Length of the angles used for the connection specified according to the surface of which they are connected. The legs are attached to the intersecting steel that make with the connections are termed web legs. Legs that are the angle of the attached supporting the intersecting steel with the beam is termed outstanding legs. Lines in which the holes of the angle legs are placed are called gauge lines. Distance between the gauge lines and known edges are termed gauges. Example complete with the connection shown figure 334. Various terms of constant dimension, standard connection, arrow angles shown figure 345. So we have a gauge line, outstanding leg, a web leg, and gauge line. Once again, the legs attached to the intersecting steel to make the connection are termed web legs. And then the outstanding legs that are attached to supporting intersected steel beams are termed outstanding legs, and you have a gauge line. Figure 335 shows standard layout connection angle using 4 by 4 inch angles. Web leg, outstanding leg, 2 3/4 inch web, 1/2 web thickness, 2 1/4 inch gauge, 2 1/2 inch gauge. And then we'll go back up here. The distance from the heel of the angle of the first gauge line on the web leg is termed the web leg gauge. The dimension has a standard 2 1/4 inch. The dimensions is constant, does not vary. Distance from the heel of the angles of the first gauge line, outstanding leg, is called the outstanding leg gauge. Dimension varies with the thickness of the member of the beam. The varies with variation necessary to maintain constant 5 1/2 inch spread dimension angle connection. Outstanding leg gauge dimensions can be determined either in one of the following two ways. Subtract the web thickness 5 1/2 inches divided by 2. Subtract half of the web thickness from 2 3/4 an inch. The distance between the holes of the end gauge line is called pitch. The dimension has been standardized at 3 inches. The end of the distance of the equal to 1/2 of the remainder left after subtracting the total of the pitch space for the length of the angle. By common practice, angle length then is selected should give you 1 1/4 inch and end of the distance. All layout fabrication procedures are not covered in this section. Some examples are shown in figure 336. Notice the layout and fabrication yard table has designed to allow the layout, cutting, welding, minimum movement of the structural member. The track materials are stored in the kinds of material. Table holders, 2 columns are fabricated out of the beam's base plates and cap plates. Angle clips or seated connections should be installed before erection. Cutting and splicing beams. At times, fabricator will be required to split a beam to make a T shape from an I shape. This is done by splitting the web. The release of the internal stress locked up within the beams during the manufacturing process causes split parts to bend and warp as the beams are being cut unless they are splitting process carefully controlled. Recommended procedure for cutting and splitting a beam is first to cut the beam into a desired length and then proceed as follows. Alright, so it shows your base plate and your seating clamps, coped angles, and cap plate. Figure 337 shows the seated connection. One making cuts up to about 2 feet long and leaving the 2 inches of the undisturbed metal between all the cuts at the end of the beam as the cut is made with the cool of the steel behind with a torch with a water sprayed with wet burlap. 2 after splitting cuts have been made, the late beam could cool the cut through the metal between the cuts starting in the center of the beam and working toward the ends following the order shown in figure 338. The procedure of splitting a beam always was very well. Splitting plate recommends when making the bars from plate. Multiple cuts for the plates can be made. Straight staggering splits procedure before cutting the space between the slits. This procedure is used to ensure the entire plate has been cooled so the bars will not warp or bend. Templates. When a part must be produced in quantity, template made first. Job laid out for the template. The template is a pattern made with a sheet of the metal, regular temper, paper, wood, or other suitable material which is used to guide the work to be done. The template can be exact size, shape of the corresponding piece as shown in figure 339. Figure 338 shows the cutting order of splitting a beam. So we have cut 1, 2, and then 3, and then 4. Use 1 and 2 for the moreover cover the portions of the piece that contain holes and cuts as shown in figure 3 and 4. The hole cuts and bends are made into the finished piece. Pilot holes, punch marks, notches, templates corresponding exactly to the desired location. Finished piece templates for the short memory plates or member template paper of same size and shape that shall be fabricated. Template angles of the fold longitudinal and along the line of the heel angle. Accurate measurement making templates shall be given the careful attention where the number of parts are produced with the template. Using inaccurate measurement making the template obviously would mean all the parts produced form it will also be wrong. Template paper is heavily cardboard material with a wax surface well adapted scribe with the rider marks. Combination of wood and template paper sometimes used to make templates. These use of wood and metal usually best choice for the templates that will be used many times. For longer members such as beams, columns, and truss members, templates cover only a connection. Templates may be joined in wooden strip to ensure accuracy. Spacing figure 339 view 1 and 2. They also may be handled separately with the templates for each connection being clamped to the member after spacing, aligning, and measuring. And making templates, same layout tools as I discussed earlier in the chapter are usually the only exemption of the marking lines, pencil, the pattern markers, knife used when punching holes in the template. Keep it in mind with the purpose of the holes, specify location and size. Therefore, a punch of single diameter can be used to all holes, and cuts are predominantly provide marking with paint. Each template is marked with a symbol mark of the piece to be used, the description of the material, the end item number of the stock material to be used in making the piece. And laying out from the template is important with the template and clamp for the material exact position. The holes are centered, punched directly through the holes in the template, and all cuts are marked. And after the templates are removed, the marks of the cuts are made permanent by rows and re-enter the punch marks. It is important each member individual piece of material be given identifying marks to identified during fabrication, fitting up the other place to form finished members. Alright, figure 339 shows paper combination templates, paper wooden strip templates, punching 2 angles being placed back to back. Paper wood strip templates, punching holes in the web of the channel. 3 paper templates, sheet iron stiffeners, cutting and punching connecting angles. And 4 paper template, cutting and punching gasket plate. 340, using a template and laying out seal channel. 1 paint marker show the flange to be cut away, coped. Center punch 2, and then 3 knots of the template indicated in the flange cope. Corresponding marks shown with the detail drawn on the direction mark used to identify locate the direction painted on the complicated member of the left hand shown on the detail drawn position shall be so they will be right side up, the member right side up in the finished structure. Assembly markers painted on each piece for the completion of the layout so that the piece can be identified during fabrication, fitting up the piece of the finished member. Pipe fitting and layout operation. Lack of the template charts, mathematical formulas need not hinder the pipe layout. With emergency welded pipes of equal diameter can be laid out field quickly, easily by using methods described here. Few simple tools you can lay out branches, Y connections, as well as turn out angle the radius numbers of segments. Few simple tools required for the both readily available familiar with steelwork through the almost daily use. Framing square in a beveled protractor about 12 inches blade, spirit level of spring steel wrapped around tape, center punch hammer, scope stone with all the needs, a staff strip of cardboard tin sheets about 3 inches wide. Also make good wrap around purposes over the discussion. Long part of the framing square is referred to as the blade, short part as the tongue. Layout per operation. 2 methods of the pipe layout commonly either 1 short method and the shop method to 1 shop method to use in field. With this Show the bearing plate, 2 the angle, 3 a girder, and 4 a truss. Method of the hand tools make layout with the pipe to be cut. One method is named so because you only use it once. The shop method will make the templates of the piece of going to with a duplicated quantity. Exact example: the job order comes into shop with 25 pieces and 6 inches pipe, all cut same angle. Obviously, it would be time consuming to use one shop method to produce 25 pieces. Hence, shop method used for the layout pattern. Patterns can be made with the template paper to get engaged sheet metal. The major advantage of thin gauge sheet metal templates where you are finished when they can be stored for later use. Keep in mind that all pipe turns are measured with the number of degrees, but it's turned from the core side of the adjacent section, straight section, angle measured between the center line and intersecting section pipe. Branch connections are measured at angle turn away from the main line. For example, the 60-degree branch is so called because the angle is found between the center line of the main pipe and the center line of the branch connection. Measures 90-degree turns, the designated number of degrees by which deviate the straight line. Quartering the pipe and laying out a joint. First step to do is set up the reference point and lines where the additional measure of the markings can be made. With this is done locating the center line, dividing it outside of the circumference pipe with the 90-degree segments, quarters, framing scale, spirit level, the soapstone. Using these procedures in the following manner: block the pipe so it can move the roll. Place the inside angle of the square against the pipe with one leg. Open one point of the center line, then underscale the distance with a half outside of the diameter of the pipe, inside angle of the square. Repeat the other part of the pipe will locate 2 points, hence the center line. By this same method, the core points also may be located, but the operation must be for any layout with the phrase for a field method. If you're using a long piece of pipe and are going to cut both ends with additional square, you will need a piece of carpenter's chalk line with a plumb bob on the H end of the 24 3/36-inch flat steel rules depending on the diameter pump to locate the top of the bottom center lines. Figure 343 shows the plumb bob rules using located top of the bottom center lines. Okay, another one-shot method of quartering pipe. Strip the paper, wrap it around with the pipe, and then tear or cut apart over the overlap. The end should be torched. Remove the paper from the pipe, fold it into the half shown in figure 344. View A, double the strip. Once again, is shown view B. This will divide the strip into 4 equal parts. Place the strip paper around the pipe. At the C markers where the ends meet, mark the pipe with a soapstone. Your pipe will be quartered. Template for a 2-piece turn. In fact, the length of the pipe square ends in the fabricated wrapping a rectangular section plate. Cylindrical form makes available the method known as the parallel form of developing pipe surfaces, hence developing lines the intersection between. So here is 344 shows locating the top and the bottom center lines, and 344 folding a tip of paper using a quartering method. Based on the principle of wraparound, templates can be made marking all manner pipe fittings for the cut preparatory to the welding. Development of the template is done with the practice of dividing circumference at the end of the view of the pipe specific numbers of equal sections. These sections are projected onto the side of the desired pipe section. Lengths of the various segments make up the pipe wall may then be laid out evenly spaced. Baseline line is in effect unwrapped circumference. Figure 345, a template available in 345 UC is wrapped around the pipe. The baseline squares with the pipe, the curved line A, B, C, D, E, F. So further, we'll locate the position cutting, making the 90-degree 2-piece turn. Draw a circle and view A equal to the outside diameter pipe with the divided half into the equal section. More accurate. Final result will be perpendicular center line bisect the drawing AI equal to the outside diameter view of the to the line. Construct the template angle TA equals to 1/2 the angle turn, in this case 45 degrees. Draw lines parallel to the center line from the points A, B, and C, so forth, and circle mark the points as they leave the line, intersect A1 with corresponding letters and extension of the AI. Little pipe distance of the drawing, straight line equal to the pipe circumference of the circle view A. This line view C should be divided into 2 pieces and divided twice as many equals semicircle A, B, and C. So fourth letter is shown. Perpendicular should then be erected from these points. The intersection will be the lines drawn point from AI view B, parallel line to baseline view C. Determine the curve of the template. A simple miter turn. After quartering the pipe, proceed to make a simple miter turn. Locate the center of the cut and point C. The general location where the cut is to be made. Upper wrap light the make line A and B complete around the pipe at right angles to the center. So here we have a view A, in this case a 90-degree turn, one 90-degree turn template at half a turn, view A, B, and C. Okay. Figure 346 shows a simple miter turn. On quarter lines, establish a baseline further layout work when you're measuring treat surface of the pipe as well as flat surface of the glass seal rule. Tape which lies against surface without kinks, even if the force still allowable. The contour of the pipe's angles also be checked for the accuracy, sighting with a square. Using a protractor square to determine the proper cutback with the desired angle of the miter turn. Start with the protractor scale set with a 0 at the parallel flat surface of the protractor blade or parallel. You can now set with the protractor for the number of the degrees desired. After you have correct setting, lock the plate on the protractor on the square with the bottom blade with the outside diameter of the pipe. Now read up the cut back of the vertical blade of the square. You must be sure the flat surface of the protractor is flush against the plate of the square. Figure 347, the outside radius of the pipe shall have then determined during the quartering operation. After you have attained the cutback measurement, make sure 1/2 of the measurement off along the center of the top of the pipe from the opposite side of the baseline measure off the same distance along the bottom of the quarter. Make a punch and marks and center punch on each side of the line. Along the side of the quarter lines, marks will be making a line pipe for the welding after the joint is cut. Using a spring steel wraparound after the joint is cut with a spring steel wraparound, pull the loop to the cut back point. Now draw a chalk line over the top of the half of the pipe through the first cut back point. Note, do not allow the wraparound to twist, link, or hold on chalk at the right angle to the wraparound while marking the pipe. Now roll this pipe 1/2 turn, mark the chalk line in the same way around the bottom half of the pipe. Figure 347 finding the cutback, number of degrees and cutback, outside diameter of the pipe. Two-piece turn. If the template is not available, you may determine the two dimensions of the marking of the cut necessary for the two-piece weld to turn angle between 1 degree and 90 degrees, making a full-size drawing as shown in figure 348. Draw center lines intersecting at B using the angle turn T to draw the outlines of the pipe using the center lines of the diameter D. These intersect at A and C by laying the pipe over the drawing so that point B will coincide with that. Determined by construction details, you can draw the level lines A, B, and CB in preparation, miter cutting, and beveling. After being prepared for the welding, one section pipe should be rotated 180 degrees tack weld and from desired angle, then should be tack welded. Spacing should be slightly greater inside of the turn. Okay, 348 should locate the cut on the pipe for angle of the two-piece turn. T is the angle of the turn, and then D is the outside diameter of the pipe. So welded teeth. Lay out the template with a cutting branch for the header of the 90-degree turn with the header of the branch equal to diameter. Draw side of the end of the view as shown in figure 349 views A and B. In making a template for a branch in figure 4, 349 view A, draw lines 145, 45 degrees and center lines. Lay out the distance 1P equal to twice the thickness of the pipe wall. Draw a smooth curve of the S, the pipe SPS. Now project point P from view A to view B. Draw with the line PT radial distance above the T to equal thickness of the header wall. Draw the AT horizontal vertical lines A and T with lower points as center springs, arcs, RSS. Intersections of these arc centers in the same radius. Draw the curved lines A, B, E, D, E, and ARID, A, E, D, C, I, B. Divide the outside circumference of the branch into equal parts of the vertical lines B, B, C, C, and so forth. Also join horizontal baseline AA. Lay out the unwrapped circumference in figure 349 view and divide each half into the same number of equal parts as the branch circumference or semi-circumference. In view, you should plot the distance AA, BB, so forth from view B. This gives the distance from the baseline to the branch, and curve of the intersection determines the location of the branch template. So here is a branch template of a view showing section pipe after cut. All patterns and all cuts radial. View showing section pipe after bevel and welded have been made. Alright, to make a template with a hole in the header, divide circumference of the header into equal parts, points 1, 2, 3, and 4, so forth. Next, project these points across view A and 349 as shown in the view C layout with line 1 through 5 and 1 equal to 1/2 the circumference of the header. Divide it into the same number of equal parts as what is done on the header. Locate P at the distance from 1 view C equal to the 1P view B, with the point P to distance 5 to 5, 4 to 4, and so forth in view as applied as shown in view and C for the curve of the template is located. Alright, branch connection. Branch header connection, figure 350 at any of the angle 45 to 90 degrees can be fabricated to the end of the equal diameter pipe with the following procedure. Over the angles less than 45 degrees can be made practical limitation imposed with the difficulty welding in the cross section. First chord of both section and pipe bear forward with the locate center line intersection point B on the header to draw lines GF the around the pipe at this point. Set the diameter FG of the blade of the square set and lock with the protractor alone 1/4 of the number of the degree of turn away with the header into, for example, the 1/4 and 60 or 15 degrees. The blade along the FG of the frost cut back measurement FA will indicate the tongue of the square measuring off the distance along the center line header line FG and mark point A described before the joint point A intersection line FG. The two sides of the quarter lines outline first cut with same protractor setting, flipping the square to mark H. Distance FH is equal to FA. FH is first portion, second cutback measurement, settings with the square upside down as compared to before. Locate I as the same way as located in point H. Now set a protractor 1/2 of the number of the degrees turn away from the header. In the example, 1/2 is equal to 60 degrees, 30 degrees. Blade set with the diameter second portion HG. The second cut measurement will indicate on the tongue the second cutback measurement of the total distance FC. Connect point C and B. Connect C with the point corresponding to B quarter line on the opposite side of the header. The outlines of the second cut completes the marking of the header. Use the same two cutback measurements. Layout end of the branch cutout distance DA equal to the header cutout distance FA. Branch cutback equal distance EC equal to the header cut distance FC. A of the branch and end square must make the cutback measurements from end rather than marking a circumferential line. Make all cuts as before. Level the joint end branch and header by welding. Weld the T branch smaller than the header. One of the best types of the joints for a 90-degree branch connection, whether the branch is smaller than their header, is obtained with inserting smaller branch pipe in the walled down inner surface of the header of the outside surface of the branch intersect the inside of the surface of the header of all points. When the header is properly beveled, the type of the intersection present, very desirable to V for welding. An easy template with a dimension of the not available line cut with both the header branch can be located with the other methods, but use templates is recommended. The first method, the square end of the branch should be placed in the correct position against the header of the line of the intersection marked on a flat soapstone pencil. Figure 351, since radial cutting is usually the case, since of the outer branch wall should intersect the inner header wall. Point B should be located on both sides of the branch. Branch A distance from A equals to slightly more header wall thickness. A new line cut then marked as a smooth curve through the points, tapering the first line at the top of the header. Following radial cut, the joint shall be beveled. The branch should be split into the hole until even with point B to locate the line of cut on the branch. A soapstone pencil may be then used to mark the line of radial cutting. No beveling is necessary. Second method, large diameter pipe is shown in figure 352. After center lines have been drawn, the branch should be placed against the header of the shown means a straight edge of the distance between A header wall is determined. This measurement above the header is transferred to the branch wall as representing the curved line A, B, and C. So we have a method of lining the cut first marked on the main. Soapstone line for radial cut. A, B, and C. Alright, after this line of radial cut, the branch may be used to locate the line of the cut header, allowing for the intersection outer branch wall, inner header walls as before. Lines shall be radially cut, followed by beveling, making a centric branch connection. Extreme case being the side of the branches, even side of the header. Similar procedure is followed and shown in figure 353. Your three-piece Y connection, entire procedure fabrication of an equal diameter three-piece Y connections based on an individual operation already described. As first step, quarter end of the three pieces of the pipe and applied circumferential lines. Where there are three pieces welded together to form a Y, there will be three center lines radiating from the common point. The opening angle between each pair of adjacent center lines must be decided. Each of these angles will angle with one of the branches of the Y, as shown in figure 354. These open angles determine the angle of the joining side of the adjacent branches, thus half the number of degrees between the center lines of B is included to each of the adjoining cutbacks between these two branches. The same is true with respect to the other angles and cutbacks between. So 352 shows the line cut first marked on the branch with this method, straight edge, A, B, and C, and D. So figure 354 shows the three-piece Y connection, protractor 50 setting 55 degrees, 80 degrees setting, and a 45 protractor setting in 90, 180, 110. Moreover, each piece must have the combination of two angles cut at the end that determine the amount of the cutback to form an angle of the Y. Set the protractor 1/2 the open angle between the adjacent branch center lines. Place the protractor on square across the outside radius. Measure the pipe and the tongue with the square. Read the cutback distance of the off the blade square. Make off the distance of the one side quarter line. Each of the two pieces that are behind the mark of the cutbacks. Complete the procedure for the other two angles of the Y, taking care of the combined cutback at each end of the pipe. The settings of the protractor determine all the cutbacks. As an alternate method, determining each cutback is true to treat two adjacent branches similar miter turn. Subtract the number of degrees to open angle between the center lines of 180 degrees. Set the protractor 1/2 of the remaining degrees. Cross the outside radius measurement and the tongue. Mark one side of each of the adjoining pipe section. Repeat the other two of the branches. Take care of the combined proper cutbacks on each pipe ending. Set the protractor for each opening of the angle of the Y connection. The computation measurements for the layout. Figure 354 is shown in Table 3.1. The pipe is 12 inches in diameter, has a radius of 6 inches, and 322 show the computation measurements of the Y computation open angle between center lines. Protractor setting half of each of the angle cutback center lines, pair cutback measurement in inches. Figure 355 shows the true Y, A, B, C, and D. Layout of a true Y and laying out a pipe for the fabrication of true Y without using templates or table. The full side of the drawing. Intersection 355 should be made with the trans intersection center line of the three pipes. We'll locate pipe B and point B lines from B to the intersection pipe walls located in the A, C, and D. From these points, the pipes may be demarked for the cutting and a miter cutting, followed by a suitable beveling necessary for preparing the pipe for pipe welding. A template layout for the true Y branch main lines and laying true template for a true Y drawing. Intersection should be made as shown in Figure 356 View A. After drawing lines at the intersection, same essential methods of the other templates are followed but not there. Suggested equally divided semi-circumferences are more conventional placed directly on the baseline. Distance for the baseline with the line of the intersection plotted on the unwrapped baseline determined on the template. The orange peel head. A number of the different types of heads are used in welded pipe construction. Here we are interested in one general type, the orange peel, since it will often concern your work, and main advantage of the orange peel is that it's high strength and resisting internal pressure. If template tables are not available for marking an original peel head, reasonable accurate marking can be secured. The following procedure for laying out template. The number of the arms for the making an orange peel head should be minimum number, which can be easily bent over to form a head of the 5 arms welds, and recommended a minimum of any pipe. This number should be increased by the large size of the pipe, dividing circumference by 5, and a good method for deciding the number of arms provided that there are at least 5. To lay out the template, draw side and end views in Figure 357. Divide the pipe circumference in View B in same number of equal parts as is planned. To have welds drawn on radial lines 0, OA, OB, and so on. Project the points A, B, and so on in this view. Alright, so this shows A, B, the template for 2 branch lines. Template for outside circumference, template for the mainline pipe. Alright, this shows a orange peel head, external circumference edge template. Now divide XO and X into equal parts on the K6, and then draw lines X1, X1, X2, X2 representing the concentric circle of UP, laying out the template distance AB, BC, A1, B1, A2, B2, so on are taken by view B. The distance X plus, X minus X1, L, X minus X2, B minus B1, and so on are taken out from the view. It is not actually necessary to draw all views A and B, and since all values can be determined in simple computation, all cutting should be radial, followed by bevel cutting. One should be field method of making an orange peel is shown in Figure 358. This method can be used when you are going to make only one orange peel. Incidentally, the table shown in Figure 358 will help you line up your template better. A field method of making an orange peel. Alright, pipe cutting. Cutting pipe is much different than cutting in the structural shape, except that you must always keep in mind with the cutting either with the radial or miter, the gas cutting torch, and use the cut pipe fittings for welding. Procedure relating to the cutting torch are given in Volume 1, Chapter 4 of the torch. May be hand operated, may be mounted on a mechanical device for more accurate control. Cutting machines may be used to prepare many of the fittings. Use the templates. These machines with cut level the bevel pipe, the operation of the bevel extent of the full pipe wall thickness. When the pipe is cut by hand, beveling is done as a second operation. For many types of welding fittings, a radial cut is required before beveling. Radial cutting simply means that the cutting torch is held so that it is perpendicular with the interior center line of all times. In other words, the cutting orifice always forms a continuation radius of the pipe, making the cut edge square with the pipe at every point. Figure 359 shows the radial cut, except in the case of the blunt bull plug for radial cut provides a proper V. Radial cut should be followed by a bevel cutting for a pipe of 3 to the 16th of an inch or more in wall thickness. In mitering cutting, the torch ship is held over the entire cut surface at the same plane. When the miter cut is followed with the beveling cut, leveling a 1/32 of an inch, 1/16 of an inch nose of the inner wall shows a mitering cut. Figure 360. 359 shows the radial cutting. 360 shows a miter cutting angle. Any pipe same system consequence will have the bends of fabricating pipe for such a system. Making bends variety of methods, either hot, cold, either manually or any. When a power bending machine, cold bends in the pipes are usually made by the bending machine. Various types of equipment are available ranging from the portable handsets or larger hydraulic driven machines so they come cold bend pipe up to 6 inches in diameter will be concerned primarily with the hot bending techniques using blending slab using a method known as wrinkling bending. Alright, templates. Whenever method you do bend pipe, you should normally have some pattern representing the desired shape of the bend. Templates made from the wire or small flexible tubing can be invaluable in preparing new installation as well as repair work. Proper made is they will provide an exact guide to the bending desired. One of the simple ties for the bend template is the center line template. A center line template is made to conform the bends of the pipe to be made. If you lay out the bend area of on the pipe as a guide during the pipe of the bending operation, show the use of the center line template. The templates are made by the wire and rod and or established shape to establish the center line on over the pipe to be installed at the end of the wire are secured to special clamps called flange spiders. Clearance disc, which must be the same diameter as the pipe if there are any doubts of the clearance around the pipe. Hot bends. Hot bends are accomplished by bending slab. Figure 362. The slab requires little maintenance beyond little coating of the machine oil. Keep rust in check. As a preliminary step, hot bending, pack the pipe with a dry sand to prevent heel outside of the bend from flattening. Flattening, of course, will reduce cross-sectional area of the pipe, restrict the flow of fluid through the system. 361 shows the center line template flange spider, clearance disc, and making allowance for the gasket. And then it shows the 362 bending of a slab, shows the heat baffle, the pull, and the dog and the template. Alright, driving a tampered board and plugging in each end of the pipe plate for the pipe with the vertical position with the plug end down. Fill it with dry sand. Leave just enough space at the upper end of the take the second plug. Ensure the hands tightly packed and tap the pipe continually with a wooden rawhide mallet during filling operation. Second plug is identical with the first, except with a small vent hole is drilled through its length. The vent permits escape for any of the gases, mostly steam. May form a packed pipe when heated and supplied. No matter how dry the sand may appear, there always is a possibility that some of the moisture is present. Moisture will form steam that will expand and build up pressure in the heated pipe unless some of the means of escape is provided. If you do not provide a vent, you will almost certainly blow out one of the plugs before you get the pipe bent. When you have packed the pipe with sand, the next step is to heat the pipe, make the bend. Mark the bend area of the pipe and check the chalk with soapstone and heat it up to even red hot along the distance indicated in the form AB figure 363. Apply heat to the bend area, frost outside of the bend, then on the outside. When even heating have been obtained, bend the pipe and conform the wire template. Template is also used to mark the bend area on the pipe. Shows a wood plug template A and B. Heating and bending pipe to conform to a wire template. Or the main problem you will have with bending of the copper tubing pipe to preventing wrinkles and flat spots. Wrinkles are caused by the compression over the pipe wall of the throat inside of the bend. Flat spots are caused by a lack of support over the pipe wall by the stretch of the heel outside of the bend by improper heating. If the pipe is properly packed and properly heated, wrinkles and flat spots can be prevented by bending the pipe in segments such as the stretch and spread evenly over the whole bend area. When a pipe is bent, the stretch tends to occur with the middle of the bend. If the bending area is divided into a number of segments, and then the bend is bent in segments, the stretch will occur at the center of each segment, thus be spread more evenly over the bend area. Another advantage of the bending in the segments is that it's almost the only way you can follow wire temper accurately. When bending steel or some other piping materials, you can control wrinkles, flat stops by first over bending the pipe slightly, then pulling the end back, figure 364. Hot bends made with the bending slab, figure 364. The pull makes the bend exerted with the direction parallel to the surface of the bending slab. The necessary leverage of the form of the bend is obtained by using a chain falls, using block and tackle, or by lengths of pipe that have large enough diameter to slip over the end of the pack pipe. Bending pins and hold down clamp dogs are used to position the bend at the desired location. Be sure to wear asbestos gloves when working on hot bending jobs. Pins, clamps, and baffles often have been moved during the bending operation. These items absorb heat from the pipe as well as from the torch flame. You can safely handle these bending accessories without proper gloves. Each material has a peculiar traits. You will need to know about these traits to get satisfactory. So overhand bending, the correct flattening of the pipe. Flatten at the throat caused by bending, overbending, pull back around and throat overbend. Result: the hints of the bending of different materials should be proof helpful. Wrought iron becomes brittle when hot, so always use the large bend radius applied with the torch to the throat with the bend inside of the heel. Brass: do not overbend a brass is likely to break when the bend direction is reversed. Copper: hot bends may be made when the copper oil is more adaptable to cold. Bending of the material is one that is not likely to give any trouble. Aluminum: overbending and reversing bending does not harm aluminum, but because there is only a small range between the bending and the melting temperature, you will have to work with care. Keep the heat in the throat at all times. You may not be able to see any of the heat color. You must depend on the field to tell you what the heat is right over the bending. You can do this in keeping a stream of the pipe while the bending area is being heated. As you see the bend starts flick with the flame and away from the area, play it back and forth to maintain the bending temperature to avoid overheating. Carbon molybdenum and chromium molybdenum. These may be heated for bending and the necessary, but caution must be exercised so that not to overheat the bend area. These types of metals are expected to easily crystallize. Extreme heat is applied. Pipes are made of these materials should be bent cold in manual and power bending machines. Hard wrinkle bends. It may be seen over after describing precautions necessary to keep the bend free of the wrinkles. We next describe the method of deliberately producing wrinkles to make means of bending the pipe. Nevertheless, you will find wrinkle bending technique a simple and direct method of bending pipe. Perhaps in many pipe bending situations, the only convenient methods would particularly be the case if no bending slab were available at the time. Consideration did not permit the rather lengthy and sandbag process. Basically, wrinkle bending consists of the simple heating operation which such a torch section pipe is heated by a gas welding torch. When the pipe becomes plastic bright red color, the pipe is bent slightly, either by hand or by means of tackle. Ridge for other purpose of the unheated portion forms the heel outside of the bend, while the wrinkle is formed on the throat inside of the bend due to the compression. It should be understood that the pipe should not be bent at a very large angle, 12 degrees being considered the maximum for one wrinkle to avoid the danger for the pipe buckling. The procedure of making large bends may vary, making several wrinkles one at a time. If, for example, you want to produce a bend of 90 degrees, minimum 8 separate wrinkles could be made. The figure 365 shows the 90-degree bend made with 7 separate wrinkles. Formula to determine the number of the wrinkles is divided by the degrees per wrinkle required within the degrees of the bend required. So it shows figure 365 shows the 90-degree bend made with 10 separate wrinkles. Wrinkle bending has successful on the pipe more than 20 inches of diameter. Experience has shown that a 7-inch diameter pipe over or more complete, even the heating accomplished using 2 or welding torches rather than one. In any event, with a heating procedure in the same torch or torches being used, heat is stripped at approximately 2/3 of the circumference of the pipe. 366 heat of the strip need not be very wide, 2 to 3 inches or 5.08 to 7.62 centimeters. Usually the vision sense of the bend will only be through 12 degrees at most. Heated portion as well. We have noted as part of the will compressed to become the inside of the bend. The portion which is not heated directly will form on the outside of the bend. Technique most often use the bend the pipe at once it has been heated. Simple and straightforward. The pipe is merely lifted up by hand or by tackle, while the other hand is held firmly in position. So 366. So the part heated before the wrinkle bend, the heated portion of the 2/3 circumference. And that completes chapter 3. Chapter 4, fiber line.